Okay, hey everybody, thanks for coming. Today's speaker is Pierre Sochala. Pierre is a researcher at BRGM, that's the French Geological Survey. He studies numerical methods and helps geoscientists apply them to various applications. If his face looks familiar, it's because Pierre visited Rasmus and Mo in 2017 for 8 months. And he's visiting again now for 10 days. He's visiting the Sustain Lab, supported by the Thomas Jefferson Fund, and we'll work together to apply Pierre's numerical methods to the data from our lab. Pierre's talk today is Uncertainty Analysis for Hurricane-Induced Storm Surge Prediction. Pierre, take it away.
Thank you, Milan, and welcome everybody. So it's a great pleasure for me to be here today to present a work done with Mo 3 years ago. And I also would like to thank the Institut Carnot for this mobility project, and as Milan said, the Thomas Jefferson for being here today. And this talk, this work is done also in collaboration with Clint Dawson from UT, and one of his students, Chen, and is about the uncertainty quantification for storm surge prediction. So the general goal of this work is to study the effect of uncertainty in hurricane propagation, and we have applied this approach on Hurricane Gustav 2008, Category 4 hurricane that hit Cocodrie in Louisiana, and I will give you some big picture about uncertainty quantification analysis. So the general framework is the following. So let's assume that you have a nonlinear model of your physical process, and it also assumes that you have a set of your input data that are described as uncertain variables. So the idea is that if you assume that you have an uncertain input, you want to propagate this input uncertainties onto the output of your model. So let's say Y in this introduction. So this uncertainty analysis requires 3 steps. The first one is the quantification of the input uncertainty. So it requires to identify the main contributors on the variability of your system and to assign them a probability distribution. The next step is to propagate the uncertainty from the input to the output, and it can be formally written as a direct relation between your output Y and your input D. And once you have this relation, you can exploit all the statistical information, such as the statistical moments, the quantile, the correlation, and the sensitivity analysis. In our case, the physical model is a storm surge model. So that is described by a set of 2 equations. The first one expresses the mass conservation equation, and the second one expresses the momentum conservation equation. And you can see that in this right-hand side of the second equation, you have 2 stresses tensor, the wind tensor and the bottom friction tensor. So these 2 tensors are modeled using quadratic parametrization, right on here. And we assume that we have, in fact, an uncertainty here in the wind speed that is useful to describe the drag coefficient. And we also assume that you have uncertainty in the friction coefficient here that is spatially dependent. In other words, it depends on the vegetation. And we will try to propagate this type of uncertainty to estimate the surge of the model.
Hey Pierre, says 3-sector based wind drag coefficient.
Yeah.
What that means?
It means that you have wind drag coefficient to the front of the hurricane, to the rear, and to the left or to the right. So this is an approach that is proposed by Powell, and this is what it is implemented in ADCIRC, in fact. But we don't use this parameterization. We don't modify this parameterization. We only modify the wind speed velocity. Okay, so the sample model is coupled to an atmospheric model, and in the spirit of a proof of concept illustration, we use the Holland model, that is a parametrical vortex model, and it has two advantages. The first one is that it is relatively simple to implement, and the second advantage is that in fact the variable in the model are provided by the best track data, because you have here the central pressure, the maximum wind speed and the radius of maximum wind speeds, and also the height of the hurricane that is useful to define the radial distance here. So all these quantities, in fact, are provided in the NHC reports. As I said before, the numerical model is an ADCIRC model, and our computational domain is represented here, and it covers the Gulf of Mexico, half of the Atlantic Ocean, and the Caribbean Sea. And we have a finer resolution in the Gulf of Mexico, especially close to the coast, to have a better resolution in the densely populated areas. So our quantity of interest is the maximum of the search over the time of simulation. So we only focus on the maximum value over time. So our quantity of interest is a spatially dependent field. Okay, the next part of the presentation will be about the strategy for the perturbation of the input, then the construction of a surrogate to approximate the relation between the input and the output, and the numerical result. Okay, so when you want to perform a sensitivity analysis or an uncertainty quantification problem, you need to first identify the main contributor. And in our case, we have many parameters, such as the trajectory, the intensity, the drag and friction coefficients. We can also want to perturb the bathymetry. So we have many parameters that we can modify, but we need to be aware that we need to deal with the well-known curves of dimensionality. So the curves of dimensionality states that if you want to approximate a function u with an error epsilon, the complexity of representation exponentially grows with the number of uncertain variables, with the dimension of your problem. So, roughly speaking, the more the uncertain parameter you have, the more the direct simulation you need to perform to have a relevant approximation of your output quantity. So keep in mind, I will talk about that later.
Yeah, what is regularity?
The regularity of the function is the way the function vary when you vary the input. So the flat function is very regular, and the heaviside function is not regular. And the
transitions between.
Yeah, and the curves of dimensionality can be mitigated by the blessing of regularity, meaning that if you have a high dimensional problem, but if the function is really regular, it's not too bad. Okay, but if you have a high dimensionality problem and irregular function, it's a nightmare to solve. Okay, once you have chosen your input parameters, you need to characterize them in sense of you need to define their ranges, distribution, and potentially their dependencies. And in our case, we need to perturb time series. So the question is, how can we perturb time series with a finite set of random variables? And our strategy to do that is the following. First, we collect the latitudes and longitude available in the base track data, and by finite differencing, we can reconstruct the meridional and the zonal velocities. So we have a matrix here of velocities, and we can standardize it to obtain, in fact, a fluctuation matrix that has a zero mean and unit variance. And after, as we need to perturb jointly the two velocity components because they are not independent, we perform an SVD. The SVD is written here, so the matrix W collect the temporal fluctuation, and these temporal fluctuations are scaled here to the matrix S and coupled to the matrix U. And in our case, we have perturbed this decomposition by perturbing the scaling matrix with this type of perturbation. Yeah?
In terms of best track data, is that like a collection of hurricanes or just this?
Just for Gustav, just for one hurricane. Yeah.
So you have series latitude and longitude, and you get, and its velocities are the displacements, like the motions
Yeah.
of the storm.
Correct.
You're trying to build a matrix to like represent, you know, for example, if it tends to go north, it's also going west, maybe, or something, some
Yeah.
correlation there.
Yeah, the resolution here is the 6 hourly best track data. So we can have an estimation of the velocity for each 6 hours.
So there's only like 30 or 40 of those, right? I mean, Gustav, that's only so long, right? So, or maybe there's 100, right? So you have like a time series of 100 motions. You're saying every 6 hours it moves, and you have a velocity every 6 hours.
Yeah, for Gustav there are 39.
Oh, okay, right. So 30.
Yeah.
That first guess was right. About
Yeah,
40.
but-
so you have a time series of 39 events.
Yeah.
And you're building I guess like a correlation matrix.
Yeah,
Yeah.
correct.
Yeah.
Yeah. But I will show you the example of perturbation just here. So here we perturb the scaling matrix with an amplitude coefficient and a diagonal matrix here depending on two random variables, xi1 and xi2. And in fact, when you perturb this matrix, we have this following result. So in red, at the middle of the profiles, you have the best track data. And in orange, you have the meridional speed, and in green, the zonal speed obtained from this type of perturbation. And after that, we can use this uncertain velocity to construct uncertain trajectory, just by integrating in time the velocity. And all this trajectory start from a deterministic location here at the west part of Jamaica, and we can appreciate the set of trajectory associated with the previous perturbation of the velocity. Okay. So to sum up the
Sorry. Okay. Alpha,
Yes.
that's arbitrary, right? That
Yeah.
alpha factor is arbitrary.
Yeah. I will explain
Sure.
the role of each coefficient. So alpha, in fact, control the width of the track, and if you take alpha equal to 0, you have the best track. If you increase alpha, you increase the width of the track uncertainty. Okay, and we have chosen alpha equal to 0.5 to produce plausible realization, in fact. About the random variables, we observe that if we consider centered random variable, in fact, the mean value of the trajectory corresponds to the best track data. And in addition, if we consider uniform distribution, we have the same probability for all the trajectory. Okay, and obviously this assumption can be relaxed, for instance, by considering other type of distribution, such as symmetrical or triangular distribution, to give highest probability for the best track data. But in our case, we use uniform distribution, and all the trajectory has the same probability to occur. So it's very nice because in fact it uses only two random variables, but it relies on the best track data, and it is only valid for in-cast mode. And we will try to change that to propose another way of perturbation for also valid for forecast mode. Any questions? Okay, so we have done the same type of perturbation for the velocity, for the maximum wind speed. So we introduce another coefficient and the random variable. So the uncertain maximum wind speed profile are represented here. So again, you have the best track in red and the random realization in blue, and the associated profile given by the Holland model as here for the wind profile. So this is the wind profile as a function here now as a radius from the eye, and here this is the pressure with a low pressure in the eye, and this is here also the radius from the center. Okay, for the bottom friction coefficient, there is no big deal in the sense that we consider two types of vegetations, marshland area and forested area, and for each we consider local perturbation with random variables from minimal and maximum values, and it's like a perturbation with random variables, so there is no technical issue with this type of perturbation.
Yeah.
Yeah.
Anthrop uses bottom friction everywhere, but here you have two options for the coefficient, which to me seem like they make sense only over land, like when you have flooding.
Yeah.
Over marshland or forest.
Yeah.
How is that? What are these values like in relation to, say, open ocean values?
And especially varying
Okay.
in the entire domain. And I think you're right. The deep ocean gives one value color, but over marsh areas, you don't know what the vegetation is. So, or at least it changes. So.
Right.
Yeah, and I think that this coefficient is important for shallow water.
Yeah.
Okay. So we can perturb differently these inputs, and a first draft was designed with eight uncertain parameters. But as I said, with the curse of dimensionality, we have finally opted for a perturbation of three variables at a time. The first scenario with a perturbation of the track and the intensity, and the second scenario with a perturbation of the bottom friction coefficient and the maximum wind. And for each scenario, we used two ensemble of simulations, one training set and one validation set, represented here. And for each point here, the hypercube here is a parametric domain, and for each point, you need in fact to run an assert simulation. Okay, so for the first scenario, the two first coordinates are related to the track perturbation, and the third coordinate is the maximum wind. For the second scenario, the two first coordinates are related to the bottom friction coefficient, and the third coordinate is related to the maximum wind. Okay, so before starting the statistical analysis, we need to validate our strategy of perturbation, and to do that we have compared, in fact, the empirical mean of the first scenario with observed values at stations on our domain of interest that includes the city of New Orleans. So we have a set of 8 stations, and we observe that the mean value given by the simulations are broadly consistent with the observation, in the sense that if we take a look in the Mississippi River here, we have a 3-meter surge. That is what we observe here. For the second station here, we have 2.5. For all the stations located at the north of the city, we have 1.5. And for this station here, we are a little bit higher for the simulation, but the difference is largely included in the variance of the simulation. So there is no problem with this station, in fact.
Jan, do you have an unperturbed control simulation? The one that didn't have perturbation?
We don't have, but my guess is that it looks like the mean, more or less. Okay. Any questions? So let's go to the statistical analysis. The question now is how, once we have the input perturbation, we need to build a relation between the input and the output, and to be honest, the only way to perform uncertainty analysis when you have a computationally expensive model is through the construction of a surrogate. So the principle of the surrogate is that you sample your domain, as I shown with the training simulations, and you rely on the input-output relation on this validation on this training simulation to build an approximation of your quantity of interest everywhere in the parametric domain. So in other words, you have some a discrete number of points in your parametric domain, and you want to fill the void to get an answer for every simulation in your parametric domain. And you can do that with polynomial chaos or Gaussian processes. And in our case, the question is, how can we build an approximation of the peak water level? Because on this picture, we only have the mean value, but we want to have the answer for any realization in your parametric domain. So the first question is, how can we deal with a random field? Okay, so we need to use the dimension reduction technique. So we use the empirical orthogonal function. So this relation, the interpretation of these terms is the following. So you have a linear combination of spatial mode, UK. The energy of each mode is given by the eigenvalue here, and the coordinate here is in fact the projection of the fluctuation onto the mode K. And in the view of surrogate construction, in fact, this relation has the following interpretation. We want, in fact, to build the fluctuation of the peak water level as a random linear combination of few deterministic vectors. So I can show you the two first dominant eigenmode for the scenario 1. So this is the first eigenmode here, and it captures 80% of the fluctuation energy. And we can see that the second mode only captures 10%. Okay, but the higher the mode, the higher the energy is. But if we change the scaling here of the second mode, we see that for the higher mode, we are able to capture lower structure, lower spatial structure. So the higher mode has less energy, but are able to capture more the detail the detail at lower structures.
Pierre, so these fields, are they like the peak water level at each point
Yeah,
throughout the whole event?
yeah,
Okay.
yeah, yeah. In fact, it gives you the main way the peak water level varies in space.
But it's not at a fixed time. It's over the entire event. You understand what I'm saying?
Yeah, because we consider the maximum value over time. So there is no time in this.
Right.
It's only a spatial.
Basically taking all your outputs and
Yeah.
building the EOFs and varying
Yeah.
those outputs.
Yeah. And to compute these quantities, we solve the following eigenvalues problem, where C is a covariance matrix. But in our case, we have the size of the covariance matrix has the size of the number of degrees of freedom of your spatial domain. So here, it's more than 100,000. So we can, in fact, build a reduced covariance matrix to compute the EOF, and it's algebraic result. So we can switch the stochastic and the physical domain to compute more efficiently these quantities. And the last question is how many terms we kept. In fact, we can we have the following results. The energy is in fact given by the eigenvalues. So if you consider all the eigenvalue, you can estimate the energy of the first eigenvalue, and you can truncate when you have enough energy. So in our case, we keep 99% for the first scenario, 95% for the second scenario. So in fact, all the variability can be taken into account through this approach, but with a limited number of modes. So it can be viewed as a compressed sensing approach. Okay, to finish the construction of the surrogate, in fact, we need to provide an approximation of the EOF coordinate, because we only know this coordinate at a finite set of observation. Okay, we have 100 simulations, so we have 100 estimation of the EOF coordinate. So we need to build an approximation of this function, relying on the observations. And we use a functional representation called the polynomial chaos expansion. And Mo already worked on this stuff. So there is many techniques to compute these coefficients. So I just mentioned that the difficulty is that we have less model evaluation than coefficient to fit. So we cannot use the squares approach, for instance, because in this case we need to have more model evaluation than this function. So you need to add fitting, L1 regularization fitting in the formulation. So this is in the problem. This is the least square fitting, but we need to add a regularization term, L1 regularization term, that gives you sparsity of the model, and everything looks good when you compare the predictive capacity of the surrogate with the true realization. I will show you the validation results obtained with the surrogate. So at the end of the day, you plug the PC approximation into the EOF approximation, and you have an EOF PC surrogate. Okay, let's go to the result. So this is the mean and the standard deviation obtained by merging the validation and training simulation. So there is no surrogate in this picture, and we can see that we have a high value in the Mississippi and in the east part of the city here, and also a high variance. And we have a moderate surge equal to 1.5 in the north part of the city. And as I said before, we have validated the surrogate by using the validation simulation. So the idea is that you check if your surrogate give you the true evaluation of the model. And this is the results on this map. And the relative mean square error is much lower than the standard deviation. This is the same unit and the same range, so we can say that the surrogate is faithful. We can integrate and we can check that in our procedure to fit the coefficient. We have a good behavior of the surrogate, and this is a technical stuff, but everything was validated to show that the surrogate is sufficiently accurate. Okay, so one important point that we want to assess uncertainty quantification is the sensitivity analysis. So we want to evaluate the effect of each input parameters onto the output. So you have a variance of your maximum water level. We want to evaluate what is the effect coming from each input parameter. So we need to quantify this effect. So in that case, if you have d parameters, in our case 3, we can decompose the output as a function of different elementary terms, and we can show that by applying this the variance operator on this function and orthogonality condition, we can show that the variance can then be in fact decomposed into first order terms, second order terms, and so on. And in our case, we have 3 uncertainty sources, so we have 7 terms, 3 first order terms, V1, V2, and V3, 3 second order terms, V1, 2, V1, 3, and V2, 3, and 1 third order term, V1, 2, 3. And we can estimate, in fact, the contribution of V1 of the first coordinate onto the variance through V1, and we can also take into account the combined effect by adding V1, 2, V1, 3, and V1, 2, 3, and we can estimate, in fact, the effect of each input variable onto the output. In fact, these variance are just normalized, divided by the variance, to obtain a sum of all the contribution equal to 1. So it's more easy to interpret. It's just a normalization. Okay, and there is suitable properties of the polynomial chaos in the sense that we can directly compute this quantity from the surrogate. Okay, this is the result of the sensitivity analysis for the first scenario. So we can see that there is no impact of the maximum wind. So it means that all the variability is given by the trajectory. But what is a little bit surprising is that there is no influence of the second variable, the variable xi2. So to understand why, we have performed a one at a time variation represented here. So on the left picture, you have the variation of xi1, but for the mean value of xi2. So xi2 is equal of its mean value, and xi1 ranges for its minimum and maximum values. And for the right plot, we have the variation of xi2 only, and xi1 is equal to its mean value. And we can see, in fact, that the variability here observed when there is a variation of xi1 is due to a variation of the beginning of the time series of the velocity. While for the second case, here, there is a very light variation in velocity, so there is no variability at the beginning of the trajectory, and all the trajectory has in fact the same values. But it was a little bit surprising, but these results, to my mind, cannot be extended to other hurricanes.
Well, so I mean, it's not a coincidence, right? It's because the way you built that matrix that these two parameters came out orthogonal to each other? Is that, it's not, it can't be luck, right? That Z1, sorry, Z1 only points along the track and Z2 only points across the track.
I think mostly it's because Gustav kind of travels in a
Well, I
straight
mean, that's the
line.
point. That's what it comes from the data.
Yeah.
Yeah, sure.
And so you build the matrix, you take eigenvalues and eigenvectors, and they're
Yeah.
going to pop out. If
Yeah.
they want to be orthogonal to each other.
Yeah. Yeah, absolutely.
So,
Yeah. If there was a recurvature in the storm, I think the two parameters would have been
Switch.
much more
Yeah.
equal, made more equal contributions to the track uncertainty.
Okay, another result that we have be interested in is the probability of exceedance of a given surge. So for a given value of a maximum surge, we can estimate the exceedance probability by computing these quantities. And obviously we have a surrogate, so we can sample it a huge number of times. So this is here the sampling with 10,000 realization, and we have used 100,000 realization here to get the exceedance probability map. So this is a map for 1 meter surge. So we observe here that the probability is close to 1 everywhere, except here. And as expected, when you increase the threshold, you decrease the probability of exceedance. And you can show that we have a high value in the Mississippi here to be lower than, to be higher than 2 meters. And obviously these results are consistent with the mean pattern that I showed before. Okay, the second scenario, the mean is roughly the same as the first one, but with a much lower standard deviation. The range here is divided by a factor 5 in comparison to the first scenario. The sensitivity indices are more equally distributed, with a high value of the maximum wind at the north of the city, because here it is Lac Pontchartrain. And we observe also that we have a strong influence of the forested and the marshland coefficient in their respective areas. Again, we can compute the exceedance probability map, and we observe here that we have a less nuanced response. So we have a binary, close to binary response. Either it is satisfied or not. So it can be appreciated here. And again, when you increase the threshold, you decrease the probability of exceedance.
I'm sorry, how are these plots different? You're changing a different parameter?
This is the maximum threshold.
Right. But you showed that plot like just like this before.
Yeah, for the difference is the scenario. This is for the second scenario.
For the what?
This one doesn't include track uncertainty.
Yeah.
Does not.
Does
Yeah.
not.
This is the second scenario with the friction coefficients and the maximum wind that are uncertain. Yeah, and it has an impact on this type of result. Okay, it's time to conclude. So, as I said, we need to repeat the procedure with different hurricanes to see if the approach is relevant, and to see what's happened with different trajectories and other abstract data. So obviously we can use more sophisticated physical model, including waves and tides and other physical process. And from a methodological point of view, the variation of the fluctuation, in fact, as we have seen, gives the same type of profile. And we can wondering if it could be, if there is a different way to perturb the time series to give more variability, because all the trajectory seems close to be parallel. So is there a way with a reasonable number of random variables to produce more realistic, not more realistic, but more with more variability trajectory with more variability. And as I said, we use the best track data, and is there a way to use the data available in forecasting just to be able to produce results in case of real life situation? And, it's an open question. So, thank you.
All right. Anybody has questions, please go ahead.
I want to give an answer. So, for number 3, I mean, you can basically take all the tracks from any different hurricanes, or you could restrict it to just hurricanes in the Gulf, for example, and get a much, basically get, thousands of data samples of displacements, right? And that would, basically give you a much fuzzier track spread. Because anytime a storm makes landfall, it's not necessarily going northwest, it could be going northeast. And
Yeah.
storms, Gustav did what it did, but there's no reason it couldn't have just turned right or left at the last minute.
Yeah, but I think that Hurricane, for instance, Irma, it changed abruptly one day before it
Right.
came close. So,
This is what Dave is saying.
Yeah,
Like,
basically, you just take, you could restrict it to storms that are in the Gulf or in the Caribbean, and just get, build that matrix from dozens of hurricane tracks instead of one. And then you would be sampling, the typical randomness of a hurricane track that's going through the Gulf. Or you could just add random noise to those tracks.
I'm just wondering if it makes sense to try to compute this matrix for all the hurricanes and to try to use all this information to do a statistical law. I'm just wondering if it's a good idea or not.
Well, I mean, essentially that's how it's done in forecasting, right? So, people make these probabilistic tracks, and they just take forecast errors, right?
Yeah.
The record of forecast errors, and accumulate them, and basically add an error of that amount every 6 hours, and create 1,000 tracks, and that's how
Yeah.
probabilistic wind forecasts are made. So,
But how?
But
does it-
the other more important question is, how do you get away from the Holland model?
glad you brought that up. Because like I said, so the one thing that really stood out to me is, your Holland wind field looks very unrealistic to me.
Unrealistic.
Very unrealistic.
Yeah.
Um,
And is it possible that the Holland model emphasizes the role of the track? Emphasizes the role of the track.
Oh, the role of the track,
Yeah,
right? Sorry.
here.
Well, let's go back to your figure of the Holland model. Like it's very early on.
Yeah.
We'll get to it.
No, actually, forward. More.
This, you want to see the Holland model?
The profile.
The plot.
Oh. The plot of what? Oh,
Back. The plot of the
There, okay. So, just an example, this is, what the Holland model tends to do is make it a very broad wind field. It's very broad at the maximum, and then in this case, you can see it's got 30 meter per second winds, or essentially what we would call hurricane force winds, out to 300 kilometer radius. Very large. Is that right?
Yeah.
So, a typical hurricane is a little more peaked and then drops and then decays.
okay,
Yeah.
yeah.
So-
you mean here?
Yeah, exactly. It'd be more like that. So yes, it's possible that could be the reason that the peak intensity isn't.
There is a
Average
shape
somewhere.
parameter. There is a shape parameter of the Holland models that we set equal to 1, and I think that this parameter can.
Right.
change.
You can use that parameter to change that, but then there are other more recently published
Yeah.
models, which unfortunately have more parameters. There's a 2-parameter model like Utility. I can give you guys the papers, but they just make more realistic wind profiles. But these wind profiles have a large effect on the surge.
Yeah.
Because that's really everything. A profile like that is going to make a large surge, and possibly a large surge over a larger, not necessarily larger at the peak point, but over a much larger area. So maybe right at your impact point, New Orleans, it's not mattering that much.
Yeah.
They will affect the maps.
Yes, if we have more sharp variation here, the effect of the track will be probably.
It'll be even more.
Yeah.
Even more. But I mean, I think that your result at the track is the most important thing. That makes sense to me anyway, and probably a lot of people here too. I mean, the track is everything, right?
Yeah.
If storm misses, and nothing happens.
Yes, but what we show is that it's all the variability. It's not 90% here. It's 100%.
Right.
All the variability due to the
Right. So another thing which tends to, for real storms tend to like, or is duration, right? So I was, the fact that I don't, if you're getting much variability in the speed at which the storm comes on shore. Because when a storm comes on slowly, then you'll tend to have surge over a longer period of time, maybe somewhat higher surge. Or if the storm races on shore, then your high surge is only confined to a very small area.
Yeah.
We weren't happy with the Holland model, but at the time, Clint was like, let's do the easy stuff first and see what happens, and then we worry about adding complexity.
Right.
And the results are interesting. So
Right.
I think we're at that stage.
Yeah.
My takeaway that this tool to me is most useful for is that after the whole UQ procedure, you can then vary one parameter at a time and explore the output. But in the deterministic model ensemble, you're sampling everywhere in the hypercube. And then using the surrogate to vary one parameter at a time tells you about the process. Do you agree? Is that to you also the?
Not really. The one at a time variation is only to have first results on how the output varies as a function of the input. But there is no interaction in this type of analysis. And if you want
Interaction between processes.
yes, between the
Okay.
inputs. Between the inputs. So the one at a time can be useful if you want to have a first guess of the variation, if it's regular or not. And, if there is no noise in your output, and but in fact the surrogate gives you all the interaction between the inputs. But obviously you can use it to take a slice in your parametric domain and to see what's
Actually, in
happening.
the beginning, we started with a five-dimensional parameter space, but
Eight.
Eight, yeah, and it became quickly apparent that the track was dominating everything else. So if you wanted to unravel it a little bit, make a story out of it, you had to separate the scenarios.
But I guess, maybe it didn't come through. So one of your points is that you did not find a large sensitivity to the maximum intensity. You did or you did not?
It's a secondary effect.
A what?
It's a secondary
It's
effect.
actually the track that dominated
Yeah.
the uncertainty by a large margin. In the first scenario, where the track was varied, it dominated the uncertainty.
Well, where do you get the range of uncertainty in your intensities from? Like if you're showing it right there, right? So basically your peak intensity only ranges from 42 to 49 meters per second, right? That's your range. I mean, is that representative of all the intensities of all the runs?
So we limited beta so that we wouldn't have a category 6 hurricane,
Yeah.
essentially.
Yes, considering this point in fact.
Yeah, so that was.
Oh, okay. I see.
Yeah, this is
wait,
variability.
What's the middle? Okay, I'm just looking at the wrong figure.
Yeah,
The
this
left
is-
figure,
This is the maximum
Okay.
wind as a function of time.
right,
And the long point is here.
right.
And the
The
red
red is the best track.
is the best
data.
track, and we have
Okay, so you do have a pretty wide range of
Yeah.
intensities at landfall.
yeah, but one of the problems for me is that all the perturbation has roughly the same structure. I mean,
Right.
As the
Same
mean,
phase.
as we perturb only the fluctuation, the mean is constant, and if it goes up here, it's supposed to go down here.
If it goes up there, it goes down.
Yeah, because we only, yeah.
Like the phase, like it doesn't change when it intensifies and when it weakens, right? It all happens at the same instant, right? The
Yeah.
curves are kind of have an envelope.
So, and where's the landfall point on that map?
Here.
Oh yeah. So what really matters is the intensities at landfall. Intensity at landfall is huge.
Yeah, anything before that doesn't.
I mean a little bit, but no.
Now, but you're pushing the winds, right? You're
But
pushing
the
waves.
high surge, you've got to have on. The wind's got to be like coming right up into the shelf. So the fact that the blue line is so tight around the red line at the landfall point, which is 901 there, right?
Yeah.
That means that you're only. Yeah.
But again, I think one of the guiding principles of this is to quantify the uncertainty for a single event. You know a storm is
Right.
coming,
Right.
so you kind of know something about the storm, and this is why we kind of focus on that event in particular.
But if you expanded that, right? If you expanded that range of values, then would you get more sensitivity or not? Or is that
Of course, you'll get more.
You will get more variability, but the sensitivity are normalized to the variance
Right.
of the
The
process.
sensitivity would be the same.
I guess, or with slight difference.
Right. The sensitivity is like increase in surge per unit per meter per second of increase in peak wind, something like that.
Yeah.
I mean,
You're saying that's not very large.
all these values reflect what you think you know, right? The sigma of the Vmax, the uncertainty in the track. So if you want to get at an output uncertainty, it should reflect what you think you know and if you have quantified it correctly. That's, from science point of view, that's the most important step. Right. If you don't know anything, you can make the range as big as you want.
Right. But in terms of sensitivity, do you have a value for the increase in surge per meter per second of increase in wind?
It's computable.
Right.
We haven't done it, but it's computable. Essentially, yeah, I think there is one. You can go to the sensitivity plot and show it. We've usually the emphasis is on the ratios. Which one dominates the uncertainty?
Right. But it's still worthwhile to know if the
Yeah, so
resulting sensitivity is right. So this is this figure here.
yeah, so this is essentially the uncertainty due to track uncertainty, psi 1, right? You could probably sum psi 1 and psi 2. It's really dominated by psi 1, and there's really very little uncertainty impact due to intensity.
Right, but it all depends on the units of C3 there, right? Because if C3 is very narrow, right, then,
C3?
I mean, I guess,
Oh yeah.
right, if that's a narrow range, then you're not going to get much.
Well, if you increase the range, you essentially get to a category 6. And this
By the
But
range,
only over, that's the problem over the ocean.
yeah.
That, the question is what is the landfall?
Yeah.
increase the range, you mean increase the coefficient.
Parameters you consider for that units, because like this, when you consider the influence of psi 3, does it include the joint contribution of psi 3 and psi 1 and psi 3 and psi 2?
Yeah, there is no in fact interaction effects.
I mean, you didn't consider, or there's no like in the cross
Because
coordination?
there is no effect.
Okay.
Yes, we have computed
Okay.
this effect, but they are close to zero. Because in fact all the variability is due to psi 1 only, so there is no interaction effect between psi 1 and psi 2, psi 1, psi 3, and psi 2 and psi 3.
Because I would think that the track would influence the influence of the maximum wind if your track is is putting your hurricane closer to your target point, the coast, then the oscillation in the wind would be more sensitive.
Anyway, this is really like relevant to the best track, and I think the more relevant question is how do you move away from the best track and worry about the more realistic distributions of the winds, right? Particularly if you actually have you're running in forecast mode, you know, the high counts.
And if you want to run in forecast mode, can you use the cone of uncertainty that are in the official forecast?
How is computed this code?
I don't know.
But you work that. No. You
Yeah,
should know.
I'm not,
You should know.
I'm working on this.
The cone of uncertainty is the average of the last 5-year forecast errors.
Oh, really? Oh.
One standard deviation.
Okay.
Not two. Only one.
And they tell you that well, they kind of give the impression that they're equally probable.
Yeah, they're computed just there's no correlation. It's just purpose. I think your intensity results are a little weird. And I think it's because you've basically built your possible intensity trajectories around the trajectory, the best track.
Yeah.
So the best track goes down to 40 meters per second at landfall. It's going to be around that. And then out over the ocean where Gustav had its maximum, if you expand that variation, then you get into this unrealistic regime. But really, it's sort of the other way around. It's at the high end, storms are really limited. They can only get to their maximum possible intensity, and they're very rare. Whereas when it's at landfall or where they're transitioning, where you get this much wider range of possibilities, where the storm could be dying, or the storm could be exploding, taking off. So I think, if you just made your tracks and your intensity trajectories much more random, had more scattered, then you can get a wider range of possibilities.
But then they wouldn't necessarily correspond to that one event you were going after.
Not that one event, yes.
Yeah.
It would tell you more about the general
Yeah.
effects.
Maybe a combination of the two would be a good idea. I don't know. Hard to say. But this is where head scratching is needed.
Any other questions? Sorry.
All right.
Down.
Yeah.
Thanks, everybody.
Thanks.